Hi everyone. This right here is the God equation of linear regression, the one and only closed form solution. For those who don't know about it, this is a one-stop equation where you can put the data matrix in X and the target vector in Y, and you have got your optimal coefficients by solving this equation. Though this equation looks a bit complex, but it holds a beautiful picture inside, which will eventually reveal why multicollinearity is never an assumption of linear regression. Suppose you are a new YouTuber and want to up your game. For that, you want to buy a new camera and a new microphone. To understand how to split your budget over your mic and cam, you want to understand the effect of them over video performance. So you have collected 1000 videos data. This is your identifier column, and you have got your feature matrix where you have two different features. One is mic price and the other one is camera price. And the last one you have got target vector, and this is your subscriber count for individual channels. Now we can see the features mic vector and cam vector in this case, and the target vector as well. If you consider the columns, these are 1000 dimensional vectors each, where 1000 is actually the number of data points we have. Now these vectors can be plotted in a 1000 dimensional space, but as we are three-dimensional beings, we have to consider this 3D space as a representative of a 1000 dimensional space. So let's plot these vectors, first mic, then cam, and then our target vector subcount. Now what we actually want to find, we want to find the optimal linear combination of the feature vectors mic vector and cam vector to get closest to the target vector, which is in this case subscriber count, right? Now if we write this in a matrix formation, it can be written in a very prompt manner. And if we go into the notation further, this is what the traditional way to write this. X denotes the feature matrix, W cap denotes the weight vector, and Y denotes the traditional target vector, which is in this case is the subscriber count. Now before we go further into this, let's have a visual understanding of linear combination of the feature vectors, as this play a key role in this whole explanation. If you have walked 5 steps in the direction of mic vector and 3 steps in the direction of cam vector, we shall be reaching at 5 into mic plus 3 into cam. This is simply coordinate system, you see. If we consider mic and cam as two different axes, then this point right here can be represented as 5, 3. Yeah, sure, you can use 5 into mic plus 3 into cam in place of this tuple, but writing this long expression every time seems kind of redundant effort, right? Now, in this fashion, if we take all the linear combinations of these two vectors, we shall eventually cover the whole plane where cam and mic vectors are lying, which is in this case is the whole screen. Now, going back to our 1000 dimensional space, if you remember, we were looking for this, the optimal linear combination. And as we have understood already, being a linear combination of the features, this is a point of the mic cam plane. Also, this point is the closest to the target vector y, which is subscriber count in this case, which is nothing but the perpendicular shadow of y over the plane. The optimal shadow vector can also be written as y cap equal to x w cap, where the w cap is the optimal weight vector. Now, what is this normal vector? You see, we can take one step in this y cap direction and then one step in the unknown normal vector direction, and then we will reach in the target vector, which is y. So clearly, the normal vector is basically y minus y cap. Now this y minus y cap vector is perpendicular over the plane, and the plane is constructed by the linear combination of cam and mic. So it's sufficient to say that y minus y cap is perpendicular to cam and mic vector both. Mathematically, we can write it in this fashion. We can take dot products of y minus y cap and cam and mic separately, and we will result into 0. Now in matrix formation, we can combine these two equations in a single matrix equation where we can take a dot product of x transpose and y minus y cap, which will result into a null vector. Doing further mathematical simplification, and voila, we have reached into our closed form solution. But the point is, what happens when instead of cam vector, we use noise suppression as the second feature? It's intuitive that the more expensive the mic is, the better will be the noise suppression. So noise suppression feature is dependent on mic feature, a classic issue of multicollinearity. So suppose noise suppression is 0.6 times mic vector. Now, as noise suppression is dependent on mic vector, it directly drops on it. This shrinks down the 2D plane into a 1D straight line. This optimal shadow point still exists, it doesn't go away. But to reach there, the path, which is the linear combination of noise suppression and mic in this case, is not unique anymore. Suppose the optimal shadow vector is 0.5 times mic, and now let's see the ways we can reach there. First, we can take 0.2 steps in the mic direction and then 0.5 steps in the noise suppression direction, and we will reach the optimal shadow point. But there are multiple other ways, right? We can take 0.8 steps in the mic direction, we will overshoot. But then we can come back, we can take a negative zero point 0.5 step in the noise suppression direction, and we will reach the again to the optimal shadow point. Another possible combination can be taking 0.1 step in the mic direction and 0.67 steps in the noise suppression direction, and there can be many more different combinations of steps. So there is an infinite number of paths to reach to the optimal shadow point, which means infinite number of linear combinations possible. Hence your budget planning is doomed. You can't distinguish how much to spend on mic and how much to spend on noise suppression separately. But you can still reach the optimal point, so it does not break the algorithm explicitly. So multicollinearity is never an assumption for linear regression, but it breaks the effectability of the algorithm. So far we have talked about shadow vectors, where we have dropped a shadow, a perpendicular shadow of the target vector over our uh, feature plane, or maybe a feature straight line if the features are dependent. So this is just the closest point to the target vector y, but when can we exactly reach y? If you have got that, please write down in the comment below. And that's all for this episode of MLBits. If you like this one, you might as well like the NLP series I have started recently. Check it out here. And if you like the content, please subscribe. Thank you. See you all in the next episode. Bye bye.